All right. How's this volume for folks in the back? Good? Sweet, thank you. All right, neural networks. So, today's lecture marks our descent into deep learning. That's what we're talking about for most of the rest of this class. Deep learning is an umbrella term for when people do machine learning with a particular type of model known as a deep neural network. And that's primarily what we're going to focus on for at least a couple of lectures is what is a neural network? Trying to understand what that is. Why are we spending so much time on this? Well, a lot of modern machine learning revolves around deep learning. It's really fueled, AI and machine learning into this, billions of dollars a year industry. So it's worth covering in some amount of detail because there's a pretty good chance that at some point or another, if you go on to do something related to machine learning, you could very well be doing something related to deep learning. So it's good to know about. So we'll spend much of our remaining time on this topic. You'll also get some hands-on experience with 2 remaining homeworks that will mostly revolve around deep learning. So that should be fun. And if you want even more, right, there's a whole class that you can take on deep learning. It's called CS182. That's another, much more detailed resource than this course in terms of spending an entire semester covering deep learning. So that's not just today. That's most of the rest of this class. But maybe it's good to back up a little bit and actually maybe try to motivate why we're going to be studying deep learning from the perspective of, a lot of, we've talked about this quite a few times already, this concept of featurization, right? So really, we're still thinking about this question that we asked at the end of lecture 1, okay? So oftentimes we're talking about, predicting Y from X. Machine learning a lot of the times is about building predictive models, but predicting from what, right? So what is X? So maybe we're given some kind of X, some kind of input. Is that the X that we necessarily want to be using directly when we're trying to make these predictions? Or is there some other better X, some better representation that's going to allow us to be a little bit more effective in terms of how we build our predictive models. What does that mean? Well, we've seen a couple of examples at this point of what that might mean. So it can mean things like, well, maybe actually what I need to do is transform X into something that's a little bit more expressive, lift it into a higher dimensionality via, for example, something like kernelization and the kernel trick. Why? Well, maybe in that higher dimensional space, I can build simple models like linear models that work better, right? That was part of the motivation behind kernelization. And we've also now seen techniques in dimensionality reduction, right? So maybe if we're given some X that's already very complicated, very high dimensional, what we actually need to do is make it lower dimensional, try to keep around as much information as possible, but reduce the dimensionality such that it's a little bit easier to work with, maybe the supervised learning algorithm can train faster, or maybe I just don't have as much noise in my data, something along those lines that actually makes the problem a little bit simpler. So we've seen both of these directions, right? Making the dimensionality higher and making it lower via kernelization and all of these dimensionality reduction techniques, respectively. And these are sort of trying to get at the question that I've posed here about what is X, right? So there's some X that you've been given, but is that the X that you need to use? Maybe there's some better representation out there that's going to make the whole system, the whole machine learning system work a little bit better. And that's really a question that lies at the heart of machine learning, is always trying to get at this fundamental question of what features should I use in order to make my system work as well as possible. So we've seen a couple of things at this point, right? We've seen kernels, PCA, all these types of things. And one thing that I think is good to sort of take away from what we've talked about so far is that if I, as a practitioner, am able to pick a good featurization, maybe I do PCA because that works well for my data, or I pick the right kernel, right? Like I inspect my data and I say RBF kernel would work well here, then I can make my models work much better, right? Maybe a linear model that wouldn't have done well in the original feature space, all of a sudden does well in this kernelized space that I've defined, right? So it's quite possible that I can take my simple models and then do something really effective with them if only I'm able to pick a good featurization. But that's a big if, okay? So one of the key sort of concerns that we're left with here is, what if I don't know how to pick a good featurization? I've only talked about a few different possible options, right? You know, a few kernels that I might be able to use, you know, PCA, which is one, you know, single linear dimensionality reduction trick. There's not actually a whole lot in this toolkit, at least that we have yet, right, that I might be able to choose from in order to pick good features. So that's kind of the key bottleneck that we still have, is that for a new problem, it might be very difficult to know how to build a good featurization with these limited tools that I have. And in general, the toolkit is limited. It's not just that we haven't had time to cover everything in this class. There's not actually a whole lot else that's commonly used besides what we've covered. So the motivation behind neural networks is that we don't always know for a lot of complex problems how to pick a good featurization, but what if instead I could learn a good featurization? So instead of saying that I have to sort of handpick, handcraft, hand design the features that I'm going to use by defining a kernel or something like that, what if instead I just define some kind of transformation that's also a learnable function with its own parameters? That function is what goes from my x to the features that I'm going to use, and then maybe I stick a really simple model like a linear model on top, and then that's going to be my full model. Okay, I'm going to learn from x to features, and then I'm going to have a really simple model that I also learn from features to prediction. And then maybe I can learn this whole thing, that I don't need to be able to hand design the right features. I can instead let the data and the model decide that based on whatever works best. So that's the high-level idea behind neural networks, is that we're going to be doing this learning of features rather than trying to design the right features. Okay, so neural networks, when you ask the question, what is X? You know, what are the features that I want to use? It takes a learning-based approach in terms of trying to answer that. That was a lot of words. Okay, then let's dive into a tiny little bit of history, okay, on what we might call feature-based learning, which is, you know, pretty similar to what we've talked about so far, and I'll give you a little bit more context behind this. Before deep learning was really popular, and by this I only mean like, you know, 10 to 15 years ago, if you wanted to deal with really complex inputs, like for example, big images, high-dimensional images, then doing this usually required a lot of feature engineering, okay, trying to pick out the right features based on whatever problem you have at hand. The techniques that we've discussed so far, like kernelization, PCA, you know, sometimes that was part of the solution, but oftentimes it didn't quite cut it in terms of getting us the best features. So a lot of the features that we picked from complex inputs had to be hand designed. Here's one example. You don't have to understand exactly what's going on here, but the high-level idea is one very popular set of features, you know, 10 to 15 years ago, for extracting features out of images was based on edge detection. Okay, so you would take little patches of your image, and then you would figure out all the different edges that you have going on in this image. And then you'd construct a histogram from those edges, and then that histogram would then become your features that you're actually using when trying to make predictions. Again, you don't have to know the details here. The high-level point is that we're not working on the images directly. We're extracting a set of features from the images based on this edge detection, okay? And then that's what we're going to try to make our prediction from. We're going to put like an SVM on top of that or something like that in order to try to make predictions, okay? This is a very popular, you know, general technique for dealing with images, you know, 10 to 15 years ago. And it was kind of, you know, pretty good in terms of, you know, having a set of hand-designed features that worked fairly well across a wide set of images, and then putting a simple model on top that we knew how to train that would be effective with those features. In some sense, we can sort of think of this as a solution that's a little bit like a compromise, okay? Because in machine learning, what are we trying to do? We're not trying to hand design, right? In machine learning, we're trying to learn from data, right? We're trying to design a model that can learn by itself the right thing to do. And so we would, you know, learn the model from the data, so we're not hand programming that part. However, we were hand programming the features, okay? So that part is not learned from data. That part is based on human expertise, on domain knowledge. And it was sort of the best that we can do as humans but it was sort of far from optimal, right? In the sense that humans are, limited in the sense of how well we can design features for a particular problem. And also, it might be the case that features that work well for one particular image problem don't work that well for another image problem, depending on what it is that you're trying to do, right? So these features, they were fairly good, but certainly it wasn't optimal by any means. The good part was that learning on top of these features was very simple. You could extract these features, like all these edges, and then collect those into a histogram, and then just pass those into an SVM, and then the SVM would kind of take care of the rest, right? So learning on top was quite simple. Coming up with good features was very hard, okay? So there was sort of, this joke that existed back in the day that, somebody's entire PhD was just coming up with a new set of features, right? And that new set of features was like a few percentage points better than the previous really good set of features. So this used to be a very, very active area of research, trying to figure out what were the best features that we could possibly build. And this goes beyond like the general techniques that we talked about, right? Like kernelization and PCA. These are very specific hand-designed features that we're trying to pick out for every particular problem that we're working on. And then maybe on top of that, we could do those things like kernelization and PCA. But the first step was to go in and try to figure out from my complex inputs, what are the features that I need, okay? That was a big part of how machine learning used to work. And in some domains, it's kind of still a big part of how machine learning works. But, we can sort of brush that under the rug, because maybe that will not be the case for much longer. Because we started to figure out how we can move from feature-based learning instead to deep learning. And the picture is something like this, right? So how we used to deal with something like images, right? We'd have our input, we'd pass that through a fixed feature extractor to get our hand-programmed features, okay? Ignore the fact that these features came from a human, and I'm showing you an image of a dog. Just pretend that it all makes sense. So we have these hand-programmed features, and what we did was we would then pass that through a learned classifier, like an SVM or something like that, in order to get our label. So this is how feature-based learning used to work. The way that deep learning came in and changed this picture was that it replaced this fixed feature extractor instead with a learned feature extractor, okay? Some other function that goes from X to features that has its own parameters that we're also going to learn. So in turn, these hand-programmed features became learned features. And as it turns out, if you parameterize the neural network in the right way, then these learned features can oftentimes be much better than these hand-programmed features that you can come up with. Okay, learning from a lot of data is oftentimes much more effective than trying to, as a human, design something that's going to work well. And also, we can learn features that are specific to the problem at hand, rather than trying to hand-design features that are general enough to work across a lot of different types of problems. Okay, so those are kind of the main benefits as we move from feature-based learning into deep learning. So let me give you a high-level picture of what this actually looks like. What is deep learning? Deep learning kind of looks like that thing on the left, if you sort of squint at it hard enough. The basic idea is we're going to be doing machine learning with multiple layers of learned representations, okay? So we're going to go from input and then transform that into some set of features, and then we're going to take that set of features, transform that again into another set of features, so on and so on and so on and so forth, which is why it's called deep, right? Because we're going deeper and deeper into our set of features until we're happy with the set of features that we have, at which point we can sort of, put a linear model on top, like logistic regression, and then make our prediction, okay? That's the basic idea of what a deep neural network looks like, and that's the basic idea behind what we're going to be trying to do in deep learning. So the function that represents this transformation, right, from our original input, like an image, into our output, like a prediction, is called a deep neural network. Okay, and deep neural networks, we'll see a whole bunch of different types of structure that deep neural networks can take. One of the key points that underlies a lot of deep learning is that the parameters for all of these different layers of learned representations are usually trained with respect to the overall objective, okay? So if I have some classification task, right, and I have the end objective, which is like accuracy, maybe I parameterize a loss, like a cross-entropy loss, like the negative log likelihood loss that we talked before, right? What I'm going to be doing is I'm going to be training all of my parameters, including in the intermediate representations, according to that objective. So how is this different than, for example, something like hand designing features and then learning a linear model on top of those hand design features? Well, that linear model is trained according to that objective, like the loss, whatever the loss is, right? But these hand design features were designed by a human. The human isn't trying necessarily to optimize that loss, right? The human is just trying to find good general purpose features. Maybe something that works well across a whole bunch of different problems, right? Like this image problem and that image problem and so on and so forth, right? So the human has a slightly different objective when they're trying to develop good features. They're trying to make them general purpose enough that they'll work well across different problems, but that also means that you might be losing some amount of optimality when it comes to trying to solve any particular problem, right? You might be getting lower accuracy than if you were trying specifically to design a feature representation that works well for this problem at hand. And so that's what deep learning is trying to do, right? In this case, we're trying to optimize all of our parameters, including the ones that are learning the features, such that it optimizes our final loss for this particular problem. And so the features can then become more specialized in solving this problem that we have. And this is sometimes referred to as end-to-end learning. Okay, so from one end all the way to the other end, right? So from inputs all the way to outputs, all of the parameters that I have in between are all going to be trained on the same objective, and that objective is whatever loss I'm trying to optimize. Yes? Would this be worse for generalization? That's a really interesting question. So it depends on the type of generalization that we're talking about. If we're talking about, the typical way that we use generalization in this course, which is like, I have the same problem, I'm just getting new data, right? Then it's not necessarily worse for generalization, right? Because, we're trying to specialize to the problem, not overfit to the training data. That's a separate problem that we have to deal with, but these sort of things are kind of separate from each other, right? If we're talking about generalization in the sense of, will features that I learn on one problem generalize to a completely new problem that has like a different specification, right? Like I'm moving from one type of classification to another type of classification, then yes, it's possible that generalization might be worse. But oftentimes what we're gaining from using these expressive deep neural networks that can learn really complex features outweighs the potential drawbacks that we might find compared to doing something like hand designing features, which generally these days just work a whole lot worse than neural network learned features. Okay, then let's actually go into a little bit of, let's start going into a little bit of math, trying to figure out what our neural network is actually going to look like. We're going to start from logistic regression because, as it turns out, logistic regression is kind of the conceptual building block that we can use to understand how we're going to build neural networks. What did logistic regression look like? Remember, it's like this linear model that we can use for classification, right? So we're given some d-dimensional input, x. Our model, f, with parameters theta, was defined as just this linear thing, right? Theta transpose x. And theta here, in particular, is going to be d, which is the dimensionality of the data, by k. K is the number of classes, right? So here I'm trying to do a classification problem over k distinct classes. For example, for something like digit recognition, it might be 10 classes, right? So then theta would be d by 10, right? So here I have a linear model. It's just a matrix multiplication between my parameters theta and my input x. And then what I get from my model is what? It's a k-dimensional vector, right? It's one number for every single one of my possible classes. And then we have to figure out, how do I actually take that, my model output, right, and transform it into a probability distribution? That's the model that I want to build. It's a probabilistic model that specifies a probability value for every possible class that this image, for example, could belong to. The way that we did that, right, remember, was using this particular function called softmax, right? So for every class from 0 to k minus 1, here we're 0 indexing, right? We define the probability that x belongs to that class C as the softmax of this model output that we're getting, okay? And a softmax function looked like this, remember? So we take all of our model outputs and we exponentiate them just to make sure that they're positive. And then we divide by the sum to normalize it into a probability distribution, right? So then this softmax is going to give me 10 numbers, for example, all between 0 and 1 that sum to 1. So that gives me my probability distribution from class 0 all the way to class k minus 1 for this particular x that I'm working with. So this is the model that I define for logistic regression. And then the loss function that I specify, I can motivate it from the perspective of maximum likelihood estimation, like we've talked about before, but the loss function might be just something like negative log likelihood loss, right? Also called cross-entropy loss, if you remember, because of its connections to cross-entropy and information theory. But this is basically the setup that we had for how we were going to do logistic regression. Just because this slide says recall does not necessarily mean that you have to remember everything here. And it's a good time to, ask questions if anything on this slide doesn't look familiar to you. So we're going to be building on top of this in order to try to figure out what neural networks are going to be. Yes? Yeah, so, right. That's totally correct. So the use of the softmax here, right, is specific to kind of this classification problem that we're trying to deal with, right? So we've stipulated that we're trying to do classification. Oftentimes, and most of the time in this class at least, when we're talking about neural networks, we're going to stick to classification because it's sort of the easiest to talk about, in which case we would want to softmax whatever output we come out with in order to define a probability distribution over the different classes. But you're totally right that we were doing something different, like, for example, something like regression. Maybe we just, have our model output a prediction directly, like the predicted target, and then we compare something like mean squared error or something like that, right? That's also motivative, also you can motivate it from like maximum likelihood estimation and things like this, but you're right that the model would look a little bit different. The high level bit here is that we're going to take some simple model, right? So logistic regression for classification or like linear regression for regression, and we're going to take that model and then slap it at the end of a neural network. And that's the high level bit about what we're doing. But you're right that this is specific to classification. When we talk about neural networks, we're going to draw pictures, because drawing pictures is so much easier than writing out math. Okay? So if I wanted to draw a picture for logistic regression, what might it look like? Well, I have my x. It's a d-dimensional vector, right? I pass it through, this matrix multiplication, which I can maybe denote as this green thing. It has its own parameters, theta. Theta is some d by k matrix, right? And then this thing, which I can, think of as like a linear layer, outputs some z, which is my k-dimensional vector, right? Here I've drawn it as the same size as x, but in general it could be very different, right? So this is kind of, what my model looks like. This is like f theta, right? F theta is this thing that transforms x to z with a single linear layer that has parameters theta. I pass this through a softmax, and that's what actually gives me my probability distribution, right? So this is what gives me the probability of every single class given x. And then I can also specify that, the way that I try to train this model is with this, cross-entropy loss or this negative log likelihood loss, whatever you want to call it, given the actual targets, given the actual labels y. Okay, so this is overall what my model looks like. I can draw a diagram like this in order to try to understand it. Yes? Yeah, great question. So I could also draw some more arrows on here, maybe like some backwards arrows, maybe like some dotted lines to make it specific that what I'm doing is like I'm doing gradient computation, right? I'm computing the gradient with respect to theta of the cross-entropy loss that I get, right? Yeah, definitely I can add more things like that into this diagram. We will, however, put off things like gradient computation until next lecture. Today we'll just focus on the structure of the model. I don't like drawing so many boxes. It's actually very tedious in Keynote So oftentimes we're going to simplify this diagram, okay? What are we going to do? We're going to omit that box that has my parameters theta in it. The parameters are in some sense implicit in the diagram because moving from something like x to z, we're going to assume has a certain set of parameters theta associated with it, okay? Just get rid of that green box entirely. Why even draw it, right? So we can just connect x to z directly with an arrow, and then that arrow is going to represent this linear layer that I'm employing. And then, forget about this lost box at the end. If we're drawing just the model, quote unquote, right, and we don't actually, care in the diagram about what the training procedure looks like, then I can just end at this particular softmax that defines my whole model from input to prediction, right? So then a simplified model might look something like this, where I just draw x, arrow, z, that denotes a linear layer, and then I pass that into a softmax. Okay, this is kind of the simplified drawing that we're going to stick with, just to make it so that I don't have to draw so many boxes and confuse everybody. All right, let's take some of what we've figured out so far and try attempt number 1 at building neural networks. So our drawing of logistic regression, maybe if we draw it in this way, it kind of suggests that logistic regression we can think of as like a single layer model, okay? It's a single layer that goes from x to z, and then we just pass that z through a softmax in order to get our probability values, predicted probabilities, right? And what we were talking about is that deep learning is really just machine learning with multiple layers of transformations. So our neural networks, just more of these layers stacked on top of each other. What if I just, instead of having a single linear layer, had lots of linear layers, right? X linear layer goes to Z1, but that's actually not my logits. I'm not going to treat them as that. I'm going to then pass that Z1 through another linear layer to get Z2, so on and so forth until I'm satisfied, right? Maybe I have L of these and I have ZL at the end. That's what I'm going to feed into my softmax in order to get my predicted probabilities. Is a neural network just a succession of these linear layers? The answer is no. There's a particular issue that comes with trying to do it this way. Does anyone know what that issue is? Yes? Exactly. So composing linear transformations together is still linear. That's the problem. If I take my x and then I hit it with some W matrix or some theta, right? And then I hit that thing with another different theta, so on and so forth, I could just combine all those thetas together and have a single big theta, right? Which is still just a linear transformation. So composing these linear transformations together, not actually particularly useful. In the end, what I get is still just a linear transformation, and that's not what I'm trying to do, right? I'm trying to learn some useful features that might be nonlinear in terms of the original data, the original x. Yes? For a single layer, is z basically the y that you had before? So they're related, right? So the z that you want at the end, regardless of how many layers you have before it, the z that you want at the end is k-dimensional, right, for classification, right? When I'm doing k-way classification, I want that final z to be k-dimensional because I'm going to pass that through a softmax and get my probabilities for each particular class, right? Usually what y denotes is like a number between 1 to k or between 0 to k minus 1 that actually tells me the identity of what class, what label this particular x belongs to. But they are related in that way. Yeah. Another question there? No. Okay. So what we need to do, actually, in order to fix this particular picture and not just end up with something that's just linear, is to make neural networks nonlinear. And this is kind of the key idea, the secret sauce behind what makes neural networks useful in terms of learning good features. So one of the main things that actually makes neural networks great or useful, right, is that they can represent these complex nonlinear functions. So the multi-linear layer thing that I showed just now can't do that, right? We need to augment our neural network in order to be able to represent nonlinear functions. How? Well, there's actually a whole bunch of different answers that you might imagine, but the answer that everybody goes with is you just add these what we call nonlinearities after every single linear layer, okay? So instead of going x, linear layer, linear layer, linear layer, so on and so forth, we're going to go x, linear layer, but then nonlinearity, before we go into our next linear layer and then nonlinearity, and so on and so forth. These nonlinearities are also sometimes called activation functions. I believe that this term is biologically inspired by, like, neurons in your brain and how they activate and things like this, but that is something that people also call them. These nonlinearities or activation functions are basically always element-wise functions. Okay, so what is an element-wise function? It means that it operates on every element in the vector separately, right? On the output of the linear layer. So the linear layer outputs some vector, right? Maybe it's k-dimensional, maybe it's some other dimensionality that we define, right? And then we have this nonlinearity that transforms every single element in that vector into some other representation, right? That's a nonlinear relationship with, the input. Some examples. You could use this hyperbolic tangent function, tan h. Okay, that basically takes in the domain from negative infinity to infinity and squashes that into the range -1, 1. You could also use something like a sigmoid, like we talked about before, right, which takes negative infinity to infinity and squashes that into 0, 1. There's another option that's very popular these days called ReLU, or rectified linear unit, which basically cuts off all of the negative numbers. Okay, so for every element in your vector, in your input vector that's negative, it just turns that into 0, and then it keeps all of the positive elements. So these are all different options that we can use in order to introduce nonlinearity. Okay, so before we had only linear transformations, now we're going to have these nonlinearities interleaved with every single linear function. Yes? That's a really interesting question. So is there such a thing as having, maybe just by definition, a nonlinear layer rather than defining it to be a linear layer plus a nonlinearity? The answer in practice is mostly no, because I think it's a little hard to imagine, or it's a little hard to define general purpose nonlinear building blocks. I think we as humans are just kind of bad at it because, like, we kind of suck at math, But I think that in particular cases there are certain types of operations that might be useful for a particular problem that would then sort of be more suitable in terms of defining an operation that's inherently nonlinear. But as far as I know, there's not anything that's sort of general purpose that kind of fits that bill. The only general purpose thing is kind of what we're describing right now, which is just linear layer and then combined with some element-wise nonlinearity. That's pretty much what everybody does. Yes? Can you define your own activation functions? Totally. Yeah. I mean, people still do this, right? I mean, like, we have a set of activation functions, like, ReLU is very popular. But then, like, people will come along and say, like, hey, here's a better activation function that I just came up with. And then sometimes, you'll have some motivation for why it might be better. But people are still sort of iterating on this and trying to figure out, like, what might be the best activation function that we have. I don't think that we've actually gotten there or anywhere close to there yet. So there's definitely still room for improvement on that front. Okay, so neural networks attempt number 2, right? Here's what we had before with some space in the middle so I can draw some other things, right? We used to have this thing where we were just successively composing linear transformations on top of one another, right? X goes to linear layer, Z1 goes to linear layer, Z2, so on and so forth. But this was no good. This actually just ends up with a linear transformation in the end. And we want something that's a little bit more expressive than that, right? So what we do is we add these nonlinearities in the middle. And again, almost all the times, these are just element-wise functions that we apply to our input. So here, the input to these nonlinearities, we've denoted as Z, right? Z with some superscript based on which layer it's at, right? We're going to call the outputs of these nonlinearities A for activation, okay? And it's, the corresponding layer that it's at, right? So Z1 produces A1 through this nonlinearity that we have. Maybe it's like a tan H, maybe it's like a ReLU, something like that. Z2 produces A2 based on this nonlinearity, so on and so forth, until you finally get to, AL, the activations at the end of your network. Usually what we do there is we do what we said we were going to do, which is slap a linear model on top of those activations, right? So we can basically treat you know, this whole thing, right, I can compress this image of linear layer nonlinearity into a single piece, which I'll just call a nonlinear layer, okay? That nonlinear layer is basically just saying I have a linear layer plus a nonlinearity. That's basically all is what it is. And I can have these successive nonlinear transformations, right? X goes to A1, goes to A2, as many times as I want, right? There's kind of a limit to how many times you might want to do this, but at the end, what I'll get is some AL, okay? These, I'm going to say, are kind of like the features that my model is outputting, okay? So I have learned features from X to AL, okay? These AL become the features that I'm going to slap a linear model on top of, right? So the final layer is linear. It looks just like logistic regression, maybe, in the case of classification, for example, right? So I slap a linear layer on top of AL. That gives me Z, which is then what I pass through into my softmax in order to get my final predictions, okay? So what we had before, right, we had logistic regression X going straight to Z, right, softmax. So all I've done is replace that X with some learned features, right? And those learned features are coming out of this neural network, this successive number of transformations, nonlinear transformations that go from X all the way to AL. That's the biggest idea. Okay, that's basically what deep learning is. Deep learning is just a whole bunch of variants on this one idea. Yes? Right, so we're transforming our X into some AL, right? And that transformation in functional form can be very, very complicated, right? Because it can be a lot of nonlinear transformations on top of each other, which is why neural networks generally are expressive, right? In terms of being able to learn AL that are maybe complex nonlinear transformations of X. And then on top of that, logistic regression or linear regression, depending on what it is that I want to do. That's pretty much the whole story, yeah. I think that's the easiest way to understand deep neural networks, is just like, I wanted good features, because good features I can put a simple model on top of, right? How do I get those good features? Turns out learning them is actually a really effective technique. So it's pretty natural to ask at this point, what the heck function even is this? Well, so we have a lot of parameters now. I'm still going to call all my parameters theta, but theta is no longer this single matrix, right, in my logistic regression model. Theta now represents all of the parameters in my neural network model, which might look like a whole bunch of sets of parameters in my linear layers. So remember, my nonlinearities actually don't have any parameters, right? My nonlinear layers, or sorry, my nonlinearities, right, I defined as some fixed function like tanh or ReLU or something like that, right? These nonlinearities don't have any parameters. The only parameters that I have are the parameters living in my linear layers, okay? The thing that goes from X to Z1, or the thing that goes from A1 to Z2, right? These are all the parameters that I have, are the linear transformations. So I can define a linear transformation, or more specifically, I can define an affine transformation, right, as something like a matrix multiplication plus adding a bias term, right? So I can take my input, which might be my X, or it might be my A from the previous layer, and then I multiply that by some W, right, which is some matrix that transforms me into my, next, whatever dimensional space I'm working with, and then I add a bias, and then that's my output of the linear layer. And then I put a nonlinearity on top of that, right, in order to make the whole thing nonlinear, right? So all of the parameters that I have are all of the W's and B's, all of the weights and biases that I have in this big network, okay? And then that, I'm going to collect all of them into a list, and I'm going to call that list theta. So theta represents all of the parameters that I have in my neural network. So if our neural network has these parameters theta, and it has L, what we call hidden layers, okay, these nonlinear layers we can also call hidden layers, then what function does it represent? It's a pretty complex function, but it's best to sort of read this from the inside out, right? So we start from X, right? And then we apply, let me actually scroll down a little bit. Okay, so we start from X, and we apply this function that we're going to call A1, What is A1? A1 is just a shorthand for this linear transformation W x plus b, okay? Because I didn't want to write out wx plus b for all of these different, layers that we have, okay? So that's just shorthand. So I take x, I feed it through my first linear layer, which I can call A1, and then I apply a nonlinearity on top of that sigma, right? And this sigma is the nonlinearity or activation function. Remember, it could be all these different things, tan h, rel u, whatever, right? And then I apply A2 on top of that, and then sigma, so on and so on and so forth, until I get to my final layer, apply AL, apply the nonlinearity again. That is my, the features that I'm outputting from my neural network, right? On top of these features, I'm actually going to do something that looks just like logistic regression, right? Which is just apply a linear layer, which here I'm calling A final, okay? And then passing that through a softmax in order to get my outputs. Actually, I just realized something. So the logistic regression model that I had before, I defined F as defined X as outputting the thing that goes into the softmax. So here, maybe it would be a little bit more consistent if I didn't have that softmax at the end. But you kind of get the idea, right? So the model is sort of outputting either the thing that's going to go into the softmax, or maybe it's just outputting the probabilities directly. So this is what that function looks like. It's a little bit absurd, right? Because this function doesn't really look like much of anything. It just looks like a bunch of complicated stuff. And I actually think that there's this XKCD comic that I really like that basically captures what we're doing here. So basically, it's this person standing on a pile of math, and then somebody standing next to them and saying, I don't know if you can read this, might be a little too small, so I'm going to read it to you. The person standing next to the person is saying, this is your machine learning system? And the guy goes, yep. You pour the data into this big pile of linear algebra, and then you just collect the answers on the other side. Well, what if the answers are wrong? You just stir the pile until they start looking right. This is basically, deep learning in a nutshell. I think that pile might be the wrong way to describe it. I think, one time Professor Sergey Levin said that it's a little bit more like a lasagna, right? Where you're kind of having these interleaved layers of different things, right? It's like a layer, linear layer, and then a nonlinearity, and then you sort of stack on top of each other, and you just kind of got to stir that lasagna until you get the right answer. This is the basic idea. So this function is not particularly pretty to look at, but it is, in essence, what a neural network is, and we're just going to be trying to learn theta, all of these different parameters, in order to try to get us our right answer, okay? And it's not pretty, but what can this function represent? As it turns out, it can represent a whole lot, okay? And that's kind of the big deal, right? That's kind of why people are interested in deep learning, is because it turns out these deep neural network models are really effective at learning a whole lot of different complex problems if you give them enough data. And we'll talk a little bit more about that issue in some future lecture, but that's the basic idea. We have these neural networks, and they're really effective at learning really good features for a lot of these complex problems, and that's why we're going to be studying them for quite some time. All right, sweet. I have enough time for this bonus section about visualizing neural network functions. There's kind of this cool website. You can go to it yourself as well and sort of play around with it a little bit. But the basic idea is you can sort of visually define, through this interface, you can define different neural networks with like different numbers of hidden layers, also like what input features you're going to put in, what's the particular data, like what's the problem that you're trying to solve, and then you just hit play, and then it trains that neural network for you, right? And then you can sort of visualize what's going on in terms of like the decision boundary and the losses and all of that other kind of stuff, okay? So we can start from, this is basically a linear neural network. It's a logistic regression model, right? There are kind of no hidden layers, 0 hidden layers, right? And what we're trying to solve is this, linearly separable problem where, we have orange on one side and then blue on the other. This is something that logistic regression should be able to handle, especially even if I only pass in sort of the original features x1 and x2, like we've denoted over there, right? So if I run this thing, logistic regression does pretty well. separates those two classes, gets very low, basically zero. Oh, it gets zero training loss and test loss. That's nice, right? So, you know, logistic regression kind of works for these types of problems. But what if I have something more complicated? So here I've changed the data set that I'm working with. Now I have something that's not linearly separable, right? I have sort of orange in these two alternate corners and then blue in the other two, right? So now I can't build a linear decision boundary that's actually going to do well, at least not in the original feature space, right? So if I run logistic regression for something like this, it kind of, you know, does poorly, right? So it kind of spreads out and predicts kind of uniform for all these different points, and then, you know, converges to a pretty high loss because the model is just not good enough at trying to you know, learn this type of problem. But what can we do when we're trying to solve these types of problems? We've seen it before, right? We can use a kernel trick, right? So we could do kernelization on this, right, in order to get more expressive features, like quadratic features. Turns out quadratic features are going to be enough in order to solve this particular problem, right? So I'm actually not even going to go all the way there. I'm not going to actually kernelize this. I'm just going to add the one feature that I know is going to help me solve this problem, which is x1, x2, okay? If I have x1, x2, then actually a linear model in that augmented space, where I have not just x1 and x2, but also x1, x2, in that space, a linear model is going to be perfectly sufficient for fitting this particular data set. And we can see that, you know, logistic regression in this augmented feature space, this lifted feature space, learns very quickly, and it kind of learns the right thing, okay? So here we have linear models in sort of non-linear feature spaces, and it's doing, you know, the right thing as long as we can sort of define the right feature space to work in. Yes? Exactly, right? So this is still handcrafted, right? I looked at the problem and I said, well, actually, if I include x1, x2 as a feature, I'm going to do really well. But how would I know in general, like when I'm working with like images or something like that, that one of these features is what I need in order to solve the problem? There's no way that I as a human can figure that out, right? So this is kind of, you know, part of the high-level motivation, but also part of the drawbacks with doing, you know, things like kernelization, right? I can solve these more complex problems even with simple models, but I need to know or figure out what the right featurization is. And a lot of the times that can be rather difficult when we're working with not toy problems like this, right? So that's nice and all. So we can solve this problem if only we were able to learn, if only we were able to figure out the right features, but figuring out the right features by hand might be very tricky, right? So instead, what we're going to try to do is we're going to try to learn those features, okay? So let's now, instead of logistic regression, define a neural network, okay, which is going to have one hidden layer. It's actually only going to have one hidden layer with, you know, the same number of what we call units or neurons as the first layer. So it's going to be, you know, 2 to 2. And then I think the activation is tan h. Yeah, it's tan h. Okay, so we have this hyperbolic tangent nonlinearity in the middle. Now, if I run something like this, actually my neural network, it's not great, but it does something a little bit more reasonable, where it's trying to, you know, sort of fit, you know, the different data that I have. And you can see that it's learning something nonlinear, right? It's not quite expressive enough to actually capture all of the data here, but it is learning some nonlinear pattern where it, you know, fits, you know, one of the blue areas, one of the blue quadrants, and it fits one of the orange quadrants, okay? So it's starting to get there, but we can see that this really, really small neural network that only has one hidden layer of 2 units is not actually quite there yet in terms of being able to represent this more complex data set that I have. So what can I do? I can do a couple of things. The typical thing that we do is we make our neural network bigger, okay? Bigger can mean either deeper, add more layers, or wider, okay? Increase the number of units in the layer. Both of these things are oftentimes very effective. Here, just to keep the visualization simple, we can just imagine making it wider, okay? So now, I'm going to expand my hidden dimension into 6, even though my input dimension here is only 2, okay? Which means that my first linear layer is basically this 2 by 6 matrix, right? That turns something 2-dimensional into something 6-dimensional. I put a nonlinearity after that in order to get these hidden activations that we have. And then from there, I go from 6 basically back to 1, right? Because I'm doing binary classification. So here, right, if I expand this, then actually what ends up happening is that I have enough, oh, there we go, expressive power to roughly learn what this data set looks like. We can see that it's not quite as perfect as if I had known ahead of time what the right features are to use, But the big benefit here is that I didn't know what features I had to use, right? So I didn't know off the top of my head that x1, x2 was going to be right. I used the original features, but I used a learned feature transformation in order to learn something that was appropriate for the problem at hand. So this is the big benefit behind neural networks. Okay, they can sort of automatically figure out what are the right features to use as long as you give them enough data and as long as you give them enough expressive capability. And so we'll talk next time about how we actually train these features in order to be useful for the problem at hand. Okay, so we'll stop there. And yeah, pick back up next time. Thanks.